Okay, good morning, everyone. Example 5 in chapter 5, AC analysis or sinusoidal steady state analysis. And this is the most important. So just to do a brief recap, we looked at 4 examples. The first 2 were about adding sinusoidal waveforms, meaning voltage or current waveforms. And the second 2 were about determining the currents for inductor or capacitor, right? So now we'll combine both of them together and we'll apply our analysis techniques to a RLC circuit, okay? So in the interest of working through this efficiently, I already have my annotations here. Students who have signed up for the class notebook automatically have access to these annotations. So the solution is already there. What I want students to do is, take notes about what I am explaining, okay? The procedure and the step-by-step methods required to solve the circuit, all right? So let's begin. What we have here is a circuit, a RLC circuit. So this is R, L, and C, right? So it's known as a RLC circuit. Values for the components already given to us. There's a voltage source in there. It is the value for the voltage source is already given to us. So the first step in a circuit like this, I always tell students, is to draw the equivalent impedance diagram. And what I mean by that is you replace each component in that circuit so that it looks like a resistor. Okay, it looks like a resistor, which is this diagram right here. So the first step, always draw out the equivalent impedance diagram. Okay, meaning every component is replaced with its equivalent impedance. And then what that does is, if you look at the circuit in isolation, if you just look at the circuit without, without any external input, meaning if you didn't know what the circuit was about and we just present it to you, it seems like a normal DC series circuit, right? You have 3 resistors in series connected to a voltage source labeled VS. That's all it is. And so the first step I always strongly recommend to students is to draw the equivalent impedance diagram, and then you can begin your analysis looking back to chapters 1 and 2. Okay, so the analysis techniques do not change. The math is different, but the techniques are exactly the same. So if you think back to chapter 2, if you have a circuit like this, you identify the components, whether they are connected in series or whether they are connected in parallel, you can determine what techniques you can apply. There are only 3 equations we use, right? Ohm's law, KVL, and KCL, right? Ohm's law, KVL, KCL. Every other technique is derived from these 3 primary equations. So in this case, since we know that the voltage source sees the 3 components as connected in series, we can reduce these 3 components to one single equivalent impedance. Again, if you think back to chapter 2, the first technique we learned was we combined resistors in series, we combined resistors in parallel, and then we took a large circuit, combined a large network of resistors, reduce it down to one single equivalent resistance, REQ. Exactly the same procedure. Here we are dealing with impedance, but impedances add up the same way as resistors, and so we can reduce it down to one single equivalent impedance. And so what we do is we remove the voltage source from our analysis. We have the open terminals, and we determine ZEQ as seen by VS. Okay, we determine ZEQ as seen by VS. You guys with me so far? Right. Now, as far as circuits go, this one is relatively straightforward. 3 resistors in series or 3 impedances in series. So the sum of ZEQ is simply R plus ZL plus ZC. And that's it. Nothing else. So now that we have set up the initial we have set up the initial steps, we can go and take a look at the voltage source. The voltage source value is given to us. We are going to compare it to our standard equation, which is V of t is Vm cos omega t plus theta, right? And from there, we can determine that Vm is 100 volts, omega is 500 radians per second, and theta is 30 degrees. If the source is not in cosine, then your first step should be converting it to cosine. So again, first step, convert sine to cosine. Because again, remember, the math is different, right? We are using complex number math. We are representing all the sources with phasors. Phasors are vectors. We need the equation in cosine format in order to write the phasor. So if the source, whether it's voltage source or current source, is in sine, then the first step should be converting the sine to cosine. Since this is already cosine, you simply proceed by extracting the information. Here, Vm is 100 volts, omega is 500 radians per second, and phase angle theta is 30 degrees. Directly write down the phasor for Vs. Magnitude 100, phase angle 30 degrees. Okay, write down the phasor for Vs. So that takes care of the sources in the circuit. Okay, that takes care of the sources in the circuit. If there are multiple sources, then you can handle them accordingly. Meaning if you were applying node voltage analysis, the procedure would be exactly the same, except it would be complex number math. Okay, so that takes care of the sources. Now let's look at the impedances. Okay, so this math is done. Impedance, ZL and ZC. R, there's no such thing as impedance of a resistor because R remains R. So ZL and ZC, you write down the equations and you plug in the values to solve it. Now, the explanation here is I will need to perform addition. I will also need to perform division. And again, if your calculators can perform these mathematical calculations in any coordinate system, then it's fine. You don't need to keep converting. For me, since I don't have a programmable calculator, I do need the rectangular coordinates and the polar coordinates for all values. So just out of habit, I developed this technique where I would determine the impedances both in rectangular coordinates as well as polar coordinates, because I will need both of them to perform these mathematical calculations. So that's why you see these double equations. Okay, so ZL is omega L with an angle of 90 degrees. That gives me the answer in polar coordinates. ZL, J omega L is rectangular coordinates. Exactly the same thing. Yes. So the question being asked is about the plus 90 and minus 90. That comes from the fact that the current for an inductor lags the voltage. Eli the Iceman, or voltage is ahead of inductor. So ZL will always be ZL. Well, Z itself is simply V over I. Voltage is ahead by 90 degrees. So when you have two phase angles being divided, for an inductor, it's always plus 90. For a capacitor, it's always minus 90. That is, let's see, what slide was that? So I would say review slide number. Yeah, this is slide number 15, page 15. Okay. So again, the direct equation for the inductor would be omega L with an angle of plus 90 or J omega L. Omega is obtained from the voltage source. Again, remember that the circuits, the inductors and capacitors and the resistors will affect the amplitude, meaning the y-axis of the voltage source or the current source is affected, and the phase is affected because there's a phase difference for an inductor and a capacitor. But nothing happens to the frequency. The frequency is not changed. Frequency remains exactly the same as the source. Okay, the frequency is not affected. So omega determines what impedance is presented by the inductor and the capacitor. In this case, omega is 500. So the impedance of the inductor at 500 radians per second is different from any other value. Same thing with the impedance for a capacitor. So you use omega as 500, you plug it into the equations, and you obtain these values. Okay. Once you have these, go ahead and determine ZEQ from here. R plus ZL plus ZC. ZC, similar to ZL, will always have an angle of 90. But because current leads the voltage, or because voltage lags the current, the impedance angle for a capacitor is always minus 90. So the equation for ZC is 1 over J omega C, 1 over J. I don't know if I showed this, but 1 over J is minus J. Here's the short derivation. So 1 over J is minus J. Reciprocal of the imaginary number is the negative imaginary number. Okay. So since ZC is 1 over J omega C, it becomes minus J over omega C. And in polar coordinates, it is 1 over omega C with an angle of minus 90. So it turns out to be the same. All right, so now you have the three values. ZEQ is simply the sum of all three. You find ZEQ. Remember, I said I'll need to perform some addition, and I also need to perform some multiplication and division. So I find the answers for the impedances in both coordinate systems. Let's take a pause while you think over all of that. Let me know if you have any questions so far. Any questions? Shall I proceed? Okay. All right, so we have ZEQ. And then I'm going to find ZEQ both in rectangular as well as polar coordinates. Again, you can transform back and forth with these. You can do so directly on your calculators. You can do it in MATLAB. You can do it manually. Again, trigonometric identities, right? So once you have ZEQ, I have the circuit reduces to this. You have a voltage source Vs, and you have ZEQ. That's it. And you can say current IS or IT or just I is flowing through the entire circuit, right? So this is an example of series parallel analysis series parallel equivalent analysis. That's the absolute first technique we learned in chapter 2. Okay. This was before node voltage analysis. Series parallel analysis, meaning you take a large circuit, reduce it down to one single resistance, find the voltage or current, and then expand it back up again step by step. That's the analysis technique that we're using here. So we find the value for I, applying Ohm's law. V equals IZ, so I is V over Z. Plug in the values, perform the math, and you obtain a value for the current. Now that value is going to be in phasor form. So if I of t is asked, as the problem states here, I of t, VR, VC, and VL. Now, it does not state that the voltages have to be in time domain. So it's not clearly or explicitly stated. But when it's lowercase, it typically means we're talking about AC voltages as a function of time. Okay. But again, if it's not stated, just to be safe, you can go ahead and find it or final answer in function of time in the time domain. So I of t would have a magnitude of 0.707 and then a phase angle of minus 15. The frequency is not affected, so the frequency remains the same. So it becomes cos of 500t. Again, I will emphasize that the frequency does not change. It is not affected by any component. So when you go back to the time domain, you use the exact same frequency that is given to you at the beginning of the problem. That does not change. All right, makes sense to everyone? Let me know if you have any questions. Now, one thing, actually, let's wait. Any questions? Okay. So one thing I'd point out is look at the phase angle of the voltage source right here, 30 degrees. And look at the total current that is flowing through the circuit. Total current I is the same for all four components. It's the same for the voltage source, the same for the RLC components. All four components have the exact same current, right? Look at the angle for that current. So voltage is as plus 30, current is minus 15. The important point I'm making here is that the resulting voltages and currents depend on how the circuit is connected and, of course, the component values themselves. Okay, so here we have three components, R, L, and C. They're connected in series. If they were connected in parallel, the resulting currents would have different angles. So depending on the values of the components, depending on the circuit configuration, the resulting currents and voltages can have any angle, could be any combination. So here there's a phase difference of 45 degrees. Okay, once you have the total current, apply Ohm's law again and determine the voltages for all three components. Again, for resistor, it's exactly the same. V equals IR. You have I simply multiplied by the resistance. That gives you the voltage for VR. VL and VC, standard equations, L di over dt. You have to perform a differentiation. For a capacitor, you have to integrate, right? You have to integrate the current to get the capacitor voltage. But because we are using complex number math, we can simply apply Ohm's law. And that's the biggest advantage of this math system. Okay. So equations are based off of Ohm's law. VR, voltage for the resistor, is I times R. VZ is I times Z, voltage of the inductor, VL, is I times ZL. And voltage for the capacitor, VC, is I times ZC. As straightforward as that. So the analysis, again, is the important point I keep making. The analysis is not new. The circuit analysis is exactly the same as what we learned in chapters 1 and 2. It's the math that is different. Okay. It's not a new analysis technique. I always want to point that out because students think about AC analysis and complex numbers, and in the past, I've seen students get apprehensive. So to lower the stress levels, I always want to point out that these are not new analysis techniques. Okay, simple Ohm's law. multiply I with R, I with ZL, and I with ZC, and you have all your values. Let's take a pause, think over everything. Let me know if you have any questions. Any questions, any concerns about the steps, the procedure? No questions? Okay. The techniques here are straightforward because it's a series circuit. If it's a parallel circuit, you apply those techniques accordingly. If it's a series parallel circuit or a parallel series circuit, you apply those techniques accordingly. Okay. So the approach for every single problem would depend on the circuit configuration. Here, what you can do also is, since it's a series connection, you can apply voltage division. Equations are already listed there. And I would strongly recommend students practice doing the math using these equations. You have the answers, you have the equations. It shouldn't take you more than 5 or 6 minutes to get through these 3. Okay, so practice outside of class, see if you can obtain the right answer or not. Again, if you have programmable calculators, it is very easy and straightforward. You simply take the values, program the equation, give you the answers. Does that make sense? Voltage division. Going back to chapters 1 and 2. And finally, the phasor diagram. Okay. So phasor diagrams can be used to plot multiple different voltages and currents. Here, what we are doing is we are plotting all the voltages with respect to each other. And because the current is the same, we only plot one current. Okay. The way to plot a phasor diagram, again, and I talked about this, you only need 2 things, right? It's a vector. So you only need the angle, you only need the length. And these are, of course, not to scale. You simply take the angle. Let's start with VS. VS is at 30 degrees. So it's an arrow that lies at plus 30. Plus 30. Positive angles rotate counterclockwise, negative angles rotate clockwise. Since the voltage source is plus 30, we are in the first quadrant, and VS is drawn right here. Then total current I is at minus 15. Minus indicates that's below the real axis, right? Minus 15 is right here. Minus means it's going clockwise. So vector is rotating counterclockwise. So if it rotates counterclockwise, it's a positive angle. If it rotates clockwise, it's a negative angle. So you get minus 15. VR is at minus 15. It goes back to the fact that the resistor does not affect the phase of the incoming voltage or the incoming current. So the phase for a voltage and the current for a resistor is always the same. So if the current is minus 15, and the voltage for that resistor is also minus 15. VR is minus 15. Impedance for a capacitor and inductor, however, is different. Inductor voltage is 90 degrees ahead of its current. Current is at minus 15. Inductor voltage VL is plus 90. meaning minus 15 to plus 75, right there. Does everyone see that? Plus 75 and minus 15. Voltage VL for an inductor is always 90 degrees ahead of the current. So it's a plus 90. Capacitor is the exact opposite. It's 90 degrees behind the current. And so it's minus 90. So minus 105. Minus 105. Does that make sense to everyone? And the reason that in this case, in this problem, the inductor voltage and the capacitor voltage is 180 degrees out of phase, exactly 180 degrees. And the reason for that is that they share the same current. Otherwise, it would be something different. Okay? If you had two inductors in the circuit, the voltage of one inductor might be maybe 15 degrees out of phase with the current for the second inductor. When we are talking about the phase shift, and I've stated this before, when we talk about phase shift, we're only talking about the voltage and current relationship for that specific component, not with reference to anything else. In this case, again, the current shared between the inductor and the current and the capacitor is exactly the same. Since the current is the same, let's take that as the baseline. Let's say 0 degrees. That means the inductor is pointing up, plus 90, and the capacitor is pointing straight down, minus 90. And hence, it is 180 degrees out of phase because they share the same current. If they did not share the same current, the phase difference between VL and VC would not be 180. It would be something else. Whatever the angle is, the approach is straightforward. It's a vector. You find the angle. Once you have the angle, just draw out arrow at that angle, mark and note the quantities, and that's it. Doesn't have to be to scale. These are not to scale. I is only 2. Magnitude of I is very, very small. It's not even 2. It's like what, 0.707. Magnitude of the current is 0.707. The voltage is 100 volts. This is not even 1 volt. 1 amp. The current is not even 1 amp. 0.707 is very low. So these are absolutely not to scale. VR is more than 100 times as long as I. Okay. All right, let's take a pause, long pause. Think over that. Let me know if you have any questions. There's a lot of information in there. But again, as I said, the approach depends on the circuit. Here it's series circuit, so we combine it. It's a parallel circuit, we combine it as resistors in parallel and then solve it. Any questions? Does the approach make sense? Okay. All right. So this is where I would say chapter 5 is at an end. There was one more thing a student brought up was the quality factor. So this is the lab that students are performing this week, right? And the quality factor refers and literally is stating the quality of an inductor or a capacitor. Okay. So let's see. One of the earlier slides, let me go there. Okay. Okay, this slide is as good as any. This is what students are doing in the lab this week. Okay, lab 6, unless your lab is ahead. Um, Ideal inductors and ideal capacitors do not have any resistance. Okay, ideal inductors and ideal capacitors do not have any resistance, meaning if you say inductor L, you're saying RL, inductor resistance, is equal to 0. But in real life, inductors will have some resistance. Remember, I said any piece of conducting wire inherently has resistance, inductance, and capacitance, but the values of those quantities do not rise to the level of interference. A wire will have resistance, a wire will have inductance, a wire will also have capacitance. But as long as it can fulfill its job of its function, then we don't really care about those values. So when we are, when engineers are designing these cables, they take those into account. Now, if you have a current carrying coil, that coil is made out of some material, that material will inherently have some resistance. So if you take the inductor like this, that is wound up in a coil, depending on the number of turns and how thin the wire is, it will have some resistance between its two ends. Meaning you take an inductor and you connect that inductor to a measurement meter, it will give you a value for that inductance L. If you take that same inductor and you connect it to a multimeter to measure resistance, it will give you a value for resistance R, because that is the resistance of that coil of wire. Okay, resistance R, this is something we haven't, maybe we talked about it in chapter 1. R is given by rho L over A. Rho is a material property. It's called the resistivity of the material that is used to make that resistance. L is basically how long that wire is. Okay, L is basically how long that wire is between the measurement terminals. And A is the cross-sectional area. Okay, A is the cross-sectional area. Resistance of that material is inversely proportional to the area and directly proportional to the length, meaning the longer the wire, the longer the resistance, and the thinner the wire, the higher the resistance. So if you have an inductor made out of very thin wire with a large number of turns, it could run into hundreds of meters long. Even a small inductor, very thin wire, could be very, very long. Okay, and so the resistance increases. So Q represents quality factor of that inductor or that capacitor. It is defined as the ratio of the reactance of the inductor to the series resistance of that inductor. The inductor, this is ideal. Let me move this side. And this would be a real life model. We cannot separate out this inductance value from the resistance. So between the same terminals of A and B, we can measure inductance and we can measure its own resistance. So this would be L, this would be RL. RL is not for load resistor right now. It stands for inductor resistance. And it is modeled as a resistor in series with that inductor. Again, I'll repeat. That resistance and that inductance is part of that same component. It is impossible. It is not possible to separate out those components. But electrically speaking and mathematically speaking, we can represent it as an inductor in series with that resistance. The ratio of the inductor reactance to that resistance is defined as the quality of that inductor. If that resistance is 0, quality is infinite. Make sense? In real life, that RL has a value of about 5 or 6 ohms, depending on the construction of the inductor and depending on the application. So high quality inductors, that is very, very low. In lab 6 in EE 251, we use inductors with low quality on purpose because we want to be able to teach students on how to perform these calculations. And so that is what you're doing in lab 6. What you're doing in lab 6 is you're verifying KVL. Okay, for those of you who are in my lab class, I go over this in detail, but those of you who are not, I will tell you right now, the lab write-up itself assumes that we're using high quality inductors. And so we add an external resistor in series with it to make the inductor bad. And all of this is in the lab write-up. All the equations that students need to solve the labs is always there in the lab write-up. So again, I always emphasize, read the few pages that are there in the lab write-up, look at the equations because it tells you everything you need to know to solve that pre-lab. So again, the labs assume that the inductors we are using are high quality inductors, meaning the resistance is very low, so you would not be able to do lab 6 without actually modeling a bad inductor. But since then, we have acquired bad inductors or low quality inductors. And so we don't have to add these. Okay. So depending on which lab room you are in, you might have high quality inductors, you might have low quality inductors. If you have high quality inductors, you have to add in an extra series resistance. If you have low quality inductors, then that inductor itself will have a resistance, and then you're adding a second resistor in series. So you have 2 resistors right there to model. Hopefully all of this is not too confusing, but that's what the Q is. Q is the ratio of the reactance to the resistance. Okay. All right. Questions about anything? All good? Okay. Then we can say that chapter 5 is at an end. And let's introduce chapter 6, frequency response. Before I begin frequency response, well, not before, actually, the first slide itself makes the point. Look at all the frequencies of some of the common electrical signals we use in everyday life. By now, everybody should be familiar, not familiar, but everybody should be able to answer that the frequency of a power outlet is 60 hertz. Outside of North America, it is 50 hertz. So there are different purposes using different frequencies. 50 and 60 are the very, very low spectrum of frequencies. In real life, we encounter frequencies that run the entire range from like tens of hertz to like millions of hertz, gigahertz, billions of hertz, even terahertz. Okay. So audible sounds, normal human hearing range is typically said like 20 hertz to 20 kilohertz. Most people are like, most people like me, I think would be like between 100 hertz to like 15 kilohertz, perhaps, not even more than that. So that's the normal hearing range. Again, those are not very high frequencies. The high frequencies start when we get into the megahertz range. Okay. AM stands for amplitude modulation. Amplitude modulation. So AM radio stations and FM radio stations broadcast at a certain particular frequency. The call sign of the radio station, 680 AM, has a technical meaning. It means the radio station is broadcasting at 680 kilohertz of frequency. 101.7 FM means it is broadcasting at 101.7 megahertz of frequency. Okay, so it has a technical name. So AM radio broadcasting is between 540 and 1600 kilohertz. FM radio broadcasting is in the megahertz range. And this is true the world over. Okay, the world over, it's implemented. Then you have cellular phones. You have television signals, mobile signals, satellite signals, um, which go into the gigahertz, the terahertz range. The two most common examples are your wireless routers, your cordless phones, your microwaves. They all run at 2.4 gigahertz. FCC, the government of every country controls the frequency spectrum, like how they control the airspace and the land and the oceans around each country. The airwaves are also controlled by the government of each country. And frequency spectrum is very precious. They auction these off every few years, and companies bid on purchasing these auctions. It's like bidding off highways. If you bid and purchase a particular frequency, only you are allowed to transmit your signals in that particular frequency. Otherwise, there's interference. It's like purchasing your own private highway. The government auctions off these highways. Companies purchase these highways for billions and billions of dollars for a particular amount of time. And then they are the only ones who get to send their trucks down these highways or their vehicles down these highways. This is how also cellular companies keep control. They lock down their phones so you cannot use them with any other network. Right? You have these signals all around you. Some of you may be using Verizon. Some of you may be using AT&T. How does AT&T prevent Verizon phones from working on their network? They lock down the frequencies, meaning the only frequencies allowed to enter the phones are AT&T frequencies. Verizon frequencies are rejected. And that rejection happens due to the magic of something known as filters, electronic filters. And as the name suggests, it filters out unwanted signals. Okay, so you'll hear me say the words signals and waves a lot. Basically represents all voltages, all currents, all functions, right? Signal simply means voltages and currents that are coming in the air. So whether it's wireless or whether it's wired, you need filters without which nothing will work. Okay, nothing will work. When you actually tune your radio station, you're actually tuning it to a particular frequency and you're filtering out everything else. When you set your radio station dial to 101.7 megahertz or FM radio station, it is only allowing that particular frequency to enter the device. Everything else is rejected or blocked. And that is called electronic filtering. Okay. So electronic filtering is what we are going to study in this chapter. So for frequency response, you're going to have to look at circuits a little bit differently. So far, the typical circuit we have looked at is you have a source of some kind, and you have like circuit components, large circuit comprising of something. You have voltages, currents. You have resistors, inductors, capacitors in the circuit. You maybe have multiple other sources, and then maybe you have a resistor or a capacitor, the inductor at the far end. Now you have to change your thinking a little bit differently. We are not going to analyze each branch current. You're going to combine two terminals of the voltage source together, and we call it a port, P-O-R-T. It's a port. And because it's a source that is supplying energy to the circuit, we refer to it as the input port. Input port. And then the output is taken on the right. That output could be across a capacitor, it could be across an inductor, it could be across a resistor. And we will study those circuits in this class, in this chapter. And then we combine both the terminals together and we call it as the output port. Input port and the output port. So this circuit can be referred to as a two-terminal, two-port network. The two terminals refer to the plus and minus. The two ports refer to the input and the output. Okay, so it can be referred to as a two-terminal, two-port network. So for this entire chapter, we have to adjust our thinking in terms of input and output. Okay. Voltage and currents are still flowing through the circuit. We will look at some of those equations, but for the large, for the large part, we have to adjust our thinking. So here's a brief example, very simplified illustration of how a filtering might work. You have a signal, and these signals can be comprised of multiple different components. Okay, multiple different components. In this case, we are stating that there's a signal that is comprised of two components, V in 1 and V in 2. Again, as I said, it's a very simplistic representation. So you have V in is comprised of V in 1 plus V in 2. And let's see. And the circuit is filtering out certain components while it's allowing other components to pass through. Okay, so the circuit affects V in 1 differently than it affects V in 2. And the way it affects it is dependent on the frequency of the incoming signal. So when we say V in 1 and V in 2, they could have different frequencies, they could have different voltages, they could have different phases. Okay, it could affect all three. The circuit could affect all three. It is not changing the frequency. It is not altering the frequency. What it is doing is it will block the signal with those frequencies from passing through the circuit. Okay, so V in 1 and V in 2, V in 1 is allowed to pass through, is actually amplified or made stronger or made larger. Whereas V in 2 is reduced. So this is made larger or amplified. And V in 2 is reduced. And then you combine both of these together at the end, and you get your V out. The circuit is actually affecting certain inputs, is not affecting other inputs. Again, this is a simplistic representation just of two components, because real life signals have multiple components. So this is something that I came up and named after myself. H of F, which is a transfer function. I didn't come up with it. I didn't name it. I don't know why they chose H of F. I guess that was the next letter in line. So maybe they chose H of F. But two things I'd like to point out, that uppercase H simply notes it's a transfer function. And more importantly, it's a function of something. What do we see? So far, we have seen V of t, I of t as a function of time. What do we see here? What is it a function of? It's a function of frequency. Remember, I said it's affecting all three. It's affecting the amplitude, it's affecting the phase, and it's also affecting the frequencies. It's affecting the frequencies. It's not changing the frequencies. It affects it in the sense that signals of a particular frequency are blocked from passing through to the output. So the transfer function of a circuit describes how the input is transferred to the output. Again, transfer function of a particular circuit describes how the input is transferred to the output. Mathematically, it's simple. H of F is simply the ratio of V out over V in. That's it. V out over V in. Nothing else. Okay, V out over V in. And if you note, all of these are phasors. H of F is also a phasor. V out and V in are phasors. Hence, H of F is also a phasor. It's a ratio of the output voltage to the input voltage. It is describing what it is going to do to the input signal. And because it's a ratio of voltages, it has no units. It is dimensionless. Okay. So we'll end class here today. We'll pick up here again on Friday. There is a homework due based on this. But again, since we have not covered the example, I will postpone that homework. Okay. That homework is going to be exactly the same as the example we do in next class, which is on Friday. It won't take long. So I will postpone it perhaps either to Friday or Saturday. Even though I don't like it and many students don't like it, you don't want to have homework due on a Saturday night. Anyway, I'll be in my office later. If you have any questions, stop by, send me an email, meet over Zoom. Otherwise, I'll see you all on Friday.